Hey, welcome back. This section we're going to be looking at initial value problems. So 1.2 initial value problems. And let's take a look. Okay. So for, in particular, for an nth order differential equation, you need n initial conditions. Okay. Differential equation. Requires n initial conditions. And you've probably already gotten a flavor of this from calculus. So for example, we're given y prime equals 2x. The solution to that is y equals x squared. You can just integrate that plus c. And if we wanted, so that's a general solution. If you want a particular solution for this first order differential equation, you need one initial condition. So let's just make up an initial condition, y of, let's say, y of 0. I'm having so much trouble thinking of an initial condition. Y of 2 equals 5. We'll try that. Okay, so I'm going to put 2 in for x and 5 in for y. So 5 equals 2 squared is 4 plus c, so c equals 1. And that gives me a particular solution, y equals x squared plus 1. Okay, so it gets rid of that c value. Okay, let's look at one of the web assigned problems here. Number 2, this is a first order differential equation. And okay, so they're going to give you a differential equation, which you technically don't even really need. All you're doing is finding the particular solution given the initial value. Here's the general solution. So let's see. And then they give you an initial condition. In this case, y of 3 is 1/5. They want you to find the solution given the initial condition. Okay, so it works just like in my last example. You're gonna, take the solution, the general solution, plop in the initial condition. So y is 1/5, x is 3, 3 squared is 9. Cross multiply, 9 plus c is 5, so c is -4. Then you just dump that into the general solution, get y equals 1 all over x squared minus 4. Sometimes they'll ask for the interval, the biggest interval that contains that initial value for the solutions. So they'll say something like give the largest interval such that the solution is defined. So you'll go to the domain of this rational expression. So to get the domain, you need to know where the denominator is equal to 0. So you go x squared minus 4 is 0. X squared is 4. So x is plus or minus root 4 or plus or minus 2. Those are the bad numbers, so you have to exclude those from your domain. So our domain will be negative infinity to -2, union with -2 to 2, union with 2 to infinity. Okay? You need to pick the domain that includes this x value up at the top, this 3. Okay? So the domain interval that includes that is this rightmost interval. So we'll use that as our interval. So the interval which contains x equals 3 is the interval from 2 to infinity. Okay? Okay, let's look at a second order differential equation. So this is problem 3, second order And for second order, you're going to need two initial conditions, right? So we have x, our differential equation, x double prime plus x is 0, which you kind of don't need. Here is our general solution. And then we need two initial conditions. Okay. So usually what will happen is you're going to need, well, first off, you're going to need to get the first derivative. Okay. So x prime is derivative cosine is negative sine, so negative c1 sine t. Derivative of sine is cosine, so c2 cosine t. Then we're going to take the initial conditions and plop them into these two equations. Okay, so we're going to take this guy and plop him in here. I'm going to take this guy and plop him in here. Okay. So you have you'll end up with two equations and two unknowns, and you could solve that system. Okay, you can always solve two equations and two unknowns, three equations and three unknowns, that sort of stuff. So let's go ahead and do that. Plugging in -1 for x. Let me go back to black. -1. That'll equal c1 cosine of t is 0 in this case. 0 plus c2 sine of 0. So I'll have -1 equals cosine of 0 is 1, so I get c1 times 1 plus c2 sine of 0 is 0. So we automatically get one of our unknowns. Let's go to the x prime equations. So plugging in x prime equals 4, and then 0 for t. Sine of 0 plus c2 cosine of 0. And again, it looks like this one works out real nice, right? So c2 is going to be 4. Right? Usually you'll have a little bit more work to do. This one just was easy. So anyways, we can write up our solution, hence our particular solution. Which conforms to these two initial conditions. So it goes through the point 0, -1, and then at the point at x equals 0, it'll have slope 4. And there's a lot more pictures in the book than I can provide here just by my writing. So make sure you're reading the book before watching the videos. Hopefully you're doing that. Anyways, hence our particular solution is going to be x equals c1 is -1, so negative cosine t, and then plus c2 is 4 sine of t, right? So I was just plugging everything back into this guy here. Okay. Okay, so there's your second order differential equation. We then turn to this idea of uniqueness and existence. So how do you know a differential equation even has a solution? You know, it's one thing to look for a needle in the haystack. It's another thing to look for the needle in the haystack if you don't even know there's a needle in the haystack, right? So in order to sort of work with the definition or the theorem that's given in the book, we're going to have to work with partial derivatives. Okay, so I just want to introduce partial derivatives. If you've seen partial derivatives before, you don't necessarily need you can probably fast forward over this part, but it may not be a bad idea to get a little more practice, right? So anyways, partial derivatives. Let's take a look. So we have an example here. F of x comma y equals 2x minus 5y plus 3. Okay, so what you're doing here is pretending one variable is a constant and the other variable is business as usual. Okay, and instead of having the regular, you know, over here to the right top, instead of having dy over dt or something, you're gonna instead of having that, you'll have a lowercase delta symbol, which kind of looks like a curly d. Okay, so that means partial derivative of y with respect to t. Okay, so we're using now this notation as opposed to this notation. Okay, so in this case, you can take the partial with respect to x or the partial with respect to y. I'll do the partial with respect to x first. So when you see the x, it's business as usual. You're doing all your Calc 1 derivative rules. When you see the y, you just pretend that that thing is a constant. Okay. So in this case, the derivative of 2x is 2. The derivative of minus 5y is 0. Okay, and then the derivative of 3 is also 0. Let's try it with respect to y. So the derivative of 2x now is 0. That x is the constant. And then minus 5y, the derivative of minus 5y is minus 5. And the derivative of 3 is also 0. Okay. So we've got about 6 examples here. Let's look at another. Okay, partial with respect to x first. So the square root y part, that's just a constant. So it's essentially like taking the derivative of 5x. You're just going to get the constant part, 5. So here, the derivative of x times this square root thingamajig is just going to give you the square root thingamajig. Let's do the derivative with respect to y. Now the x part is constant, so you just kind of leave that part alone. Let's rewrite this so it's easier to take the derivative, doing the power rule. So bring down the 1/2 y to the negative 1/2, and then we can clean it up a little bit. Okay. Let's get another. So z equals ln of x squared plus y squared. Okay, partial of z with respect to x. So for the derivative of the natural log, you go 1 all over the guts times the derivative of the guts. So with respect to x, the only variable then is the x squared. So the derivative of that is 2x. The derivative of y squared, that's just 0. Clean it up a little. Okay. Let's do the partial with respect to y. It's pretty much the same thing. 1 all over the guts times the derivative of the guts. So x squared, its derivative is 0. Y squared, its derivative is 2y. This next one always seems to give people trouble because of the way it's written. People want to do like the quotient rule on it or something. It's not necessary. So the trick to this is just kind of rewrite everything with negative exponents. Okay. And then let's do the derivative. Another way of writing a partial derivative, so for example, the partial derivative of z with respect to x, you just write z and then put a little x there. Okay. All right, so here the x squared is the part we got to take the derivative of. So that's 2x. Leave the other stuff, it's just constants. Plus, now you're doing the derivative of x to the negative 1, so you bring on negative 1. X to the negative 1 minus 1 is negative 2. Rewrite it, make it look pretty. And there's our first partial. Let's get the other. So in this case, you could write zy if you want, z sub y. Okay, so bring down the negative 1, so negative 1/2, leave the x squared alone, y to the negative 2. And then plus, bring down the 2, so 6y, x to the negative 1, make it pretty. Negative x squared, 2y squared. Plus 6y over x. Okay. One more. Okay, so we have z equals e to the y sine of xy. Okay, so the partial with respect to x, e to the y is just a constant, so you're basically just going to have e to the y, and then take the derivative of sine as cosine, and then you need a chain rule, right? So times the derivative of xy with respect to x is just y. We usually don't like to put things behind the cosine function because it's confusing as to whether or not this y here, this factor, is inside the cosine, especially if you don't use parentheses around your the xy here. Some people don't. So I'm going to put the y in front just for readability. it's in your best interest to make your work readable, because there are people going to grade your work, right? And if they misread your work, they can mark it wrong. Okay. So anyways, the second guy, you're going to need a product rule. So I'll take the derivative of e to the y first. Derivative of e to the y is e to the y. Leave sine xy alone. Plus, take the derivative of the sine xy. So leave e to the y alone. Derivative of sine xy is cosine xy, and then chain rule times x. Okay. Let's rewrite that as well. Okay. So finally, we can go to the high-powered existence uniqueness theorem. The book doesn't really give much of an explanation beyond just here it is. Don't feel bad if you don't understand why this is true. I think you would have to take some more math. Okay, so it's not something like, oh no, I should have learned how to. No, don't worry. This is advanced stuff. Okay, so anyways, theorem 1.2.1. This will apply to the following type of differential equation. So given dy, this form, dy over dx equaling some function of x and y, and some initial condition y of x sub 0 equals y of 0. There's going to be a unique solution if two criteria hold, and it will work on a particular interval. So let me draw out this region they're going to reference in the definition. So we're going from A to B and then C to D. So it's like some box region. And they're going to call the box region R in the definition. So I put R here in red. And within this interval from A to B, there's going to be this I sub 0 interval. So maybe put that in blue. So we'll just call it I sub 0. And okay, so let me write it out. If we have this f of xy, this differential equation, and the partial of that thing with respect to y, if those things are continuous on that box, then there will exist unique, well, there exists an interval, interval I sub 0, and a unique function y of x on this I sub 0 that is a solution to the IVP. Just for completeness, writing it out, it's important to really investigate your theorems. If you get ambitious, you could probably Google it, and somebody out there, I'm sure, is more capable of explaining it than I am. But anyways, let's look at example 5. Again, the example 5 in this section, what they do is kind of talk about example 4 from the previous section. So recall example 4 from 1.1. I know you probably don't remember it. Let me write it out. So they give you this differential equation, dy over dx is xy to the 1/4. And then they gave you a solution, y equals 1/16 x to the 4th. But we said there was also a singular solution, which is y equals 0. So if you were to plot both of those solutions in the xy plane, you would see that at the point 0, 0, there is not a unique solution. Right? So let me graph y. So y equals 1/16 x to the 4th is like a flattened parabola. That looks like this. Ugh. And then y equals 0 is like this. So in particular, at 0, 0, there is not a unique solution. Okay. So if you were to look at these criteria, you would see that they don't hold at that point. So let's look at the criteria in this case. And the f of x comma y thing that they're talking about. And so these are the two criteria that we need to hold. The f of xy thing is this guy right here. Okay? And then we need to take a partial of it and check for continuity. Okay, so let's note that. So notice f of xy equals, that should be x y to the 1/2. Oops, the daisy, sorry. So notice f of xy is xy to the 1/2. And let's get the partial of f with respect to y. That'll equal 1/2 xy to the negative 1/2. Let's rewrite it. So we get x over 2 square root y. F of xy, it's continuous everywhere greater than 0, and it's continuous from, I guess, the right side at 0. This is continuous 4, let's say, rather. Y greater than, or maybe even equal to 0 if you include continuity from the right. This other guy, though, is definitely not continuous at 0. So this is continuous for y values greater than 0. And that's why, okay, so you really couldn't claim at all that there's going to be a unique solution at 0, 0, because the y coordinate is a 0 there. There may be, unique solutions out here if you're looking at the picture and I'm putting these other dots. We know for a fact there's not one at 0, but at these other points there could be. So the theorem isn't saying that there's no way there is a unique solution when this criteria, when the criteria doesn't hold. It's just saying that you can't guarantee there's going to be a unique solution there. And they talk about that in the book, and at the end of the section they always have little factoids. Okay. So right, let's look at one of maybe we should look at one of these from my math lab and see what they look like. It is WebAssign. Sorry, it's WebAssign. No, yeah, or WebAssign. We only have 2 softwares and I can't keep them straight. Sorry, I wasn't already logged in. I'm slipping. Look at the student view. What the heck is, I don't care what that is. 2520, go. Sorry, we're in 1.2 right now. We'll make this question the video quiz as well. So this is the video quiz, video quiz, video quiz, video quiz, video quiz, video quiz. Okay, so let's look at number 10. Determine the region of the xy plane for which the differential equation would have a unique solution whose graph passes through a point x0, y0 in the plane. So get 9 minus y squared, y prime equals x squared. Okie dokie. So I need to find my f of xy, my partial. So f of xy is just going to be, you could do that by solving for y prime, right? So you get x squared. 9 minus y squared. This thing is going to be continuous wherever the denominator is not 0. Okay, so you could take 9 minus y squared and set it equal to 0. So y squared is 9, so y is plus or minus 3. So our interval on this guy, negative infinity to negative 3, union negative 3 to 3, union with 3 to infinity. And then we want the partial of this thing with respect to y. Okay. So probably want to rewrite this. Let me smush this in. X squared 9 minus y squared to the negative 1. Sorry about that. And then to take the derivative, you bring down the negative 1, so negative x squared times 9 minus y squared to the negative 2 times the derivative of the guts there. That's the chain rule, so negative 2y. And what is that? That'll be 2x squared y all over 9 minus y squared squared. That's the same domain. So negative infinity to negative 3 union with negative 3 to 3 union with 3 to infinity. And that is with regards to the y value. X can be anything you want it to be in this case. It's not going to give you any issues with regards to continuity. Okay? Sometimes it does. We could look at one more and see how that is. But this is the video quiz question. So anyways, a unique solution will exist so long as y is less than negative 3, y is in between negative 3 and 3. Sorry, I smushed that in there. And y is greater than 3, which is what you see as my answer over there. Let me make that look a little prettier. Sorry about that, it's just driving me nuts. So negative 3, y less than 3. Okay. Okay. Let's maybe look at one more. This is number 11. X squared plus the same kind of problem, I guess. Y prime equals y squared. So our y prime, which is the f of xy, will be y squared all over x squared plus y squared. Okay. We're worried about continuity again. The only place where you're going to have an issue with continuity with this expression would be when both x squared and y squared are equal to 0. Okay. So we're kind of looking for where that happens. The only place that happens is at the origin. Okay, so x comma y, I guess if you wanted, you say can't equal 0, 0. Okay, let's get the partial. Maybe I need a little more room for that. Let me rewrite this first. So this is y. Well, I guess maybe we should do low d high minus high d low, right? So let's get the partial of f with respect to y. Low, x squared plus y squared, d high, 2y minus high, d low, all over the low squared. And then simplify, so 2x squared y plus 2y cubed minus 2y cubed, x squared plus y squared squared equals 2x squared y. And it's the same place, right? It's the origin is the only place it's not going to work. It's continuous everywhere else. So again, xy can't be 0, 0. Hence, a unique solution exists everywhere except at the origin. Okay. Okay, so hopefully that makes some sense. Let's see if there's anything else I want to hit. Well, yeah, just to recap with regards to intervals, because it seems like we threw a bunch of intervals in your lap. There's the domain of the solution phi of x, which is basically just where that thing works, right? So it's just finding. It has nothing to do with the differential equation. It's just here's the solution. What is its domain? Secondly, then the interval of definition. Okay, which we called I. And that's where the solution is defined, and then all of its derivatives are continuous up to the order of the differential equation. Right? So nth order differential equation, you have to have n order all the way up to the nth order derivative being continuous. Okay? And then thirdly, now we have the interval of existence and uniqueness. which is I sub 0. In general, in the book here, we won't make too big of a deal out of this stuff. We kind of just assume that we're in a good place, but we should note that these things are general. They can be all different. Okay. So it's just an interesting topic. Anyways, I think that will do us. You should be able to hopefully get through the homework. And as usual, thank you for watching, and we'll see you next time.